Okay, now let's take a look at absolute configurations at tetrahedral centers. We talked about enantiomers before and how they are non-superimposable mirror images of one another. And a specific enantiomer may be indicated by its optical rotation, such as plus tartaric acid, which means what? That it's dextrorotatory. It rotates plane polarized light in a clockwise direction. Or minus tartaric acid, which rotates plane polarized light in a counterclockwise direction, levorotatory. So optical rotation is a property that can be distinguished or that can be measured, and it distinguishes one enantiomer from its mirror image. They have opposite directions of rotation of plane polarized light. But it does not define the spatial arrangement of atoms about the chiral center. We use the absolute configuration to make this designation. The absolute configuration describes the spatial arrangement of the four groups about a chiral center. So, for instance, 2-butanol has a chiral center. 2-butanol has this chiral center right here. It has a pair of enantiomers with different spatial configurations. So we have what's called the S enantiomer and the R enantiomer. And you can see that these two molecules are mirror images. They are not superimposable. If you build models of these two, you cannot rotate one and make it look like the other one. Two groups of the four on that carbon will not match up. So we have two different three-dimensional configurations around that chiral carbon, and one is designated as R and one is designated as S. So we have S2-butanol and R2-butanol. How do we assign R and S? How are these two configurations defined? Well, we assign priorities 1, 2, 3, and 4. And we use the Cahn-Ingold-Prelog Rules. And you might remember these from when we were defining an alkene as an E or a Z. We put the low priority group, which is 4, one is the high priority group. We put the low priority group in the back, behind the chiral center. With that in the back, we consider the arrangement of the top three priorities, 1, 2, and 3. Are they in a clockwise arrangement? Are they in a clockwise arrangement? 1, 2, 3. Then this would be R. Are they in a counterclockwise arrangement? 1, 2, 3. 1, 2, 3 would be counterclockwise. That is S. So here we have a chiral carbon. We have our chiral carbon here, and we have our priorities 1, 2, 3, and 4. Now, 1 is the top priority, 4 is the low priority. And what is it we're supposed to do? We're supposed to put the low priority group in the back. Now, models really help. And I'll show you later how you can do this with models, but do it quickly so you don't have to spend a lot of time building complicated structures. But sometimes people, many people, including myself, are able to just visualize looking at this structure from different angles. So you could look from below, picture yourself lying down, looking up from underneath, and what would you see? The carbon with group 4 behind it. I'll make this bigger. So group 4 is behind the carbon, and this is the chiral carbon. And if you were to lie down underneath this and look up, group 2 would be going up. Group 1 would be going down to your left. And group 3 would be going down to your right. And you would say, oh, this is 1, 2, 3, and it's clockwise, so this would be R. You can also rotate, instead of picturing yourself lying there, rotate this so that the 4 tips backwards, the 2 tips up, and then you have this picture I drew to the right. If we look at this case, we have our carbon with group 4 behind. This is from looking below. Now 3 would be up, 2 would be down here, and 1 would be here. And we have counterclockwise, which is S. Here's another way to look at this. We want to get the low priority group in the back. And one thing you can do is create an axis of rotation. So here I'm going to rotate along this bond between the chiral carbon and the high priority group in this case. I'm nothing special about the high priority group. It's just that that's located along this axis. And if I rotate it, 4 comes down to here, 3 goes from the back to the front, coming out at you, and 2 rotates up top. So group 1 is along the axis. It didn't rotate. The wedges and the dashes are in the same locations, but now 2 is here, 4 is here, and 3 is here. And 4 is on a dash, which means it's going back. And that's all you need, is for it to go back. It doesn't have to be directly behind the carbon like I drew in the last 2 examples. This is clearly going back behind the chiral carbon. It's just rotated slightly so that you can see it. So now that that's back, when I go from high priority 1 to 2 to 3, it is clockwise, and that is R. Again, some people can pick up on these 3-dimensional structures right away. Other people need some practice. And so building models, getting used to tetrahedral geometry is one way to gain a little experience. And then after a while, you'll probably not need the models as much. So what do R and S stand for? Well, they come from Latin. So R is rectus, which is Latin for right. And so the idea is if you put the low priority group in the back, if you think of starting here at 12 o'clock and you go clockwise, it's going to the right. If the low priority group is to the back and you have a configuration like this, then from 12 o'clock up at the top here, starting there, this counterclockwise rotation from the top is going to the left. And so that is S for sinistra. It does not stand, these do not stand for Rick Sobers.